We will now see the calculation of the other variable importance measure used in random forests, the MDA, mean decrease in accuracy. The principle of the MDA is as follows. We want to evaluate the decrease in predictive performance of a forest when we noise up a variable. To illustrate the calculation of the MDA, let us suppose that a random forest has already been trained. Consider the following test set composed of 5 observations, D input variables, and a continuous variable y. Let us compute the MDA of the variable x, j. To do this, we consider the 5 values of this variable on the test set represented here in green. We will build a modified test set in which the values of xj are permuted. This modified test set is shown below. The values in orange are nothing more than a permutation of the values of the variable xj in the initial dataset. So we have 2 test sets, an initial test set above and a modified test set below. We then calculate the error of the forest, e.g. its quadratic risk, on each of these 2 test sets. The difference in these risks is the forest MDA for the variable xj. Intuitively, if the MDA of the variable xj is close to 0, it means that swapping the values of the variable xj has no influence on the predictive performance of the forest. Conversely, if the MDA value is large, it means that the error on the swapped test set is much larger than the error on the original test set, which means that swapping the variable xj had the effect of decreasing the predictive performance of the forest. As with the MDI, the MDA should not be computed with a training set which was used to build the forest, but rather on a test set. It is interesting to note that the ways of calculating the MDA differ according to the software used. The procedure for computing the MDA that we have just presented is the simplest. It consists in dividing the dataset into a training set on which the random forest is trained and a test set used to evaluate its performance. A test set in which the values of the considered variable are swapped is created. The difference in the predictive performance of the forest between this swapped test set and the initial test set is thus the MDA. Another method of calculating the MDA based on the out-of-bag error can also be used. For this, the MDA of each tree is calculated as follows. Consider the dataset composed of the 5 observations presented here and consider the first tree of the forest. Let's imagine that this tree is built from data 1, 3 and 4 of the initial set. This means that data 2 and 5 are not used to build the tree and can therefore be used as a test set for this tree. We can then swap the corresponding values of the variable xj, here 9.2 and 6.7, compute the performance of the forest on this swapped dataset, and compare it to the performance of the forest on the initial set. This allows the MDA to be computed from data that was not used when the tree was constructed. For this calculation method, the MDA of the forest is simply the average of the MDA of each tree. By default, the MDA calculation in scikit-learn is based on splitting the dataset into a trained set and a test set. The MDA is easily used via the permutation importance function. Computing the MDA does not require retraining the forest and is therefore quite fast. Unfortunately, the MDA, like the MDI, is biased in the presence of correlation. On the other hand, the quantity to which the MDA converges is not relevant, either for the purpose of variable selection or for the purpose of identifying the links between the input variables and the output variable. In summary, you should not use either MDI or MDA as implemented in the packages because we do not know what quantity MDI converges to, and we know that MDA converges to an irrelevant quantity either for model selection or for identifying links between inputs and output, two of the most classic goals in machine learning. Nevertheless, alternatives exist. Other procedures compute the MDI on a test dataset, thus removing the bias from using the same dataset to learn the forest and assess significance. The research papers presenting this method are available here, and the modified MDI code is available via this link. One way to compute the variable importance in order to do model selection is to retrain a random forest by removing the variable in question. The difference between the predictive performance of the forest with all variables and the one built without the variable in question allows to evaluate the contribution of this variable. This technique, statistically relevant, is very costly in terms of computation time because it requires retraining a forest for each variable. Alternatives exist to estimate this relevant quantity for model selection. You can look at the last article mentioned here, which presents an algorithm called Sobol MDA. In summary, the purpose of variable importance is to better understand how a model's prediction is constructed. However, the real goal is not to understand the random forest, but the real link between the input variables and the output variable, not the link between the input variables and the output of the random forest algorithm. The theoretical results show that MDI and MDA do not identify the true relationships between the input variables and the output variable. Also, remember that these importances have no intrinsic interest. Their relevance depends on the problem you are trying to solve. Understanding variable importance is a current research issue. Alternatives to classical measures are proposed, including those presented here, and I strongly encourage you to use them. On the other hand, variable importance is only meaningful when the predictive performance of the model is good. If the model has poor predictive performance, i.e. if it fails to capture the true link between the inputs and output, variable importances show which variables are related to the prediction without guaranteeing that these variables are in fact related to the output variable.